mistake of telling some people what my title was going to be. Turns out, for reasons that I'll touch on in a moment, for reasons that I'll touch on in a moment, that yes, I have to slightly revise what I want to talk about today. In very broad terms, what I want to discuss is part of a larger project. So, in very rough terms, and I think what I mean by this will hopefully become clearer as I go along, this larger project is interested in figuring out what the kind of minimal mathematical structures are that you need to do physics, where physics here is, certain specific physical theories. And so, in particular, physics by and large is up to its eyeballs in real numbers, but we recognize, of course, that there's a kind of conventionality about our use of the real numbers. Particularly the reals. That's relative to choices of scale or choices of units. That suggests that we ought to be able to do physics without making those kinds of conventional choices. What does doing that actually look like? There's an obvious kind of resemblance here to field programming. I mean, even this kind of idea that we're going to try and do physics without numbers, science without numbers, if you will. This isn't coming from a kind of nominalist motivation. I mean, I'll talk about motivations in a moment. So Eddie Cumming Chen has done some similar work, and he's talked about this as the intrinsicalist vision in distinction to Field's nominalist vision. What that means is that whereas Field kind of wants to do without not only real numbers, but also things like properties. It also means that, and as David Malamud pointed out, that it's much harder for Field to talk in a kind of nominalistically acceptable way about possibilities. I don't have those kinds of constraints, so I'm a lot more relaxed about the sort of metaphysical resources that I'm happy to help myself to. I'm also, although I think this is somewhat independent, as we'll see, a bit more relaxed about the kind of mathematical resources that I'm willing to help myself to, and certainly the kinds of ways that I am interested in doing mathematics. So, I mean, the broad picture here is that we're trying to find the intrinsic skeleton that underlies our physical theories. This is also, I thought, kind of Halloween appropriate.
Neil, if you hit that thing on the screen, you can get rid of the meeting is recorded.
Oh, yes. Yeah, because it's not being recorded, right?
It is being recorded, but I won't share it.
Ah, yes, that's what we agreed. Good. Yeah, good. Yeah, please don't.
Just to blackmail you.
Exactly.
For my private use.
Good. So I think it's probably worth saying a little bit about why you might want to do something like this. This is, I think, particularly acute given that Hans kind of yesterday told us the extent to which trying to find these sorts of artifact-free representations thinks a will o' the wisp, and so which is what this painting is. Invite you all to follow me into this nonsense. I thought it was worth trying to say why, although I disagree with Hans about very few things. I mean, this might not even be a disagreement. Let's hope. So there's a few motivations. So one is a motivation of wanting to get a sort of clear or perspicuous sense of the structural commitments of your physics. So what are the parts of your physics that are really doing work as opposed to being kind of conventional or calculational conveniences and so on and so forth. So the same sort of motivation that lots of people think is an advantage of coordinate-free geometric methods compared to coordinate-based geometric methods. I think many people in this room, don't really want to think about that as a difference in metaphysical sort of setup. But I do think that we get insight, at least by having, not even necessarily because I think the sort of picture I'm sketching here is more insightful than the normal physical picture, but it is a different picture. And I think having two pictures insight than having one. Secondly, I've already sort of touched on this, is we want to maybe try and avoid making conventional choices and presenting the theory. The third motivation, and again, hopefully it'll become clear what I mean by this as we go along, is that doing physics in this way enforces a certain kind of conceptual hygiene, because the mathematical structures you're working with are more limited. So the kinds of operations that you could do are generally kind of reduced. And so you have to it sort of forces you to check that your I's have been dotted and your T's have been crossed, because the kinds of things that you might be able to do mathematically in sort of normal ways of doing physics turn out to not even be sort of mathematically allowable. You're kind of confined to just the physically meaningful operations. And the fourth motivation is that the mathematics that you use turns out to be kind of cool. So that's also just fun. Good. Okay, so let's talk about what we're going to do today. So as I say, this is a broader project. So I have a paper that is forthcoming in BJPS that sketches doing this kind of thing for the case of Newtonian mechanics. And then I thought, okay, cool. Well, next thing, again, actually partly motivated by famously the fact that, as David Malaman pointed out, this is kind of tricky for field, was to think about quantum mechanics. But in order to do that, I kind of realized that was trying to bite off more than I could chew, and so I needed really to think about Lagrangian and Hamiltonian mechanics. That's what I was going to present today, and then in the course of trying to do this, it's become clear that I would need to think in quite a bit of detail, just doing the sort of differential geometry part. You need, in order to talk about Lagrangian or Hamiltonian mechanics, requires quite a lot of thought. I also just ran out of time to make slides, and I'd made the ones about differential geometry, but hadn't made any ones about Lagrangian mechanics. And so I kind of just truncated the presentation there. As this might suggest, this is all at a very early stage of development, so I'm very open to ideas. A bit like David said yesterday, part of my motivation for presenting this is partly that it does relate to the themes of the workshop, but also that this audience is an audience that I feel happy to present early stage work to, and hopeful and confident that I'll get a lot of useful feedback on where I should go with it. Good, so here's what we're going to do. So first of all, I'm going to introduce these sort of intrinsic characterization of scalar and vector quantities. That's just building on my previous work. We're just recapitulating in a slightly more streamlined way some of my earlier work, and then talk about how to apply this to differential geometry. Good. So, the starting point is going to be the idea of a scalar quantity. So when you do undergraduate physics, people tell you, well, look, a scalar quantity is anything that takes value. It's a thing that just has magnitude, but does not have direction, in contrast to vector quantities. The difficulty, as I say, is that the real numbers intuitively have too much structure to really represent the space of possible mass values, right? So then the question is, well, how do we get rid of that excess structure? It turns out the simplest way to get rid of that excess structure, I think, is to observe that although a claim like the mass of this object is 2 is not physically significant, the claim this object is twice as massive as this other object is physically significant. And so basically, what you want is a structure that will recognize those sort of ratio facts, but will not recognize anything else. And so actually the simplest sort of definition to characterize is where you're dealing with what I'll call a full scalar quantity. So this, intuitively speaking, is one that looks like the real numbers, except you just got rid of that excess structure. Moreover, it's one that does not distinguish between the two cones of its possible magnitudes. So an example would be spatial displacement. So we don't think there's any kind of intrinsic difference between a spatial displacement in one direction and spatial displacement in the other. Electrical charge, at least insofar as you have charge conjugation symmetry, you don't think there's really an intrinsic difference between positive charge and negative charge. But there is like a relational difference, as it were. You need to have both positive and negative charges in there. So that means that you should represent those things using a one-dimensional vector space. That's pretty easy. A signed scalar quantity is a one-dimensional oriented vector space, so a vector space where you have kind of imposed a mathematical difference between the two vector spaces, as it were. Intuitive examples of this are actually not a little bit thin on the ground, but we will be using these things at various points. But if you think there's an arrow of time, then time displacements would be an example of this, because there's an intrinsic difference between a future-directed and directed interval. Right? So if you have kind of Tim Maudlin's view on the methodicity of time, for example. And then finally, a positive scalar quantity corresponds to those quantities that, where you've only got one half of the vector space. So mass, for example, because at least in elementary physics, you don't have negative masses, you don't have negative lengths, you don't have negative durations. Mathematically, so one way to characterize this is as just one half of a one-dimensional vector space. That's sort of yeah, probably I don't know, there's a lot to be said about that way of doing it. If you want, a slightly more, conceptually hygienic way of doing it is as a principal homogeneous space over the multiplicative group of the real positive real numbers. What that means is basically that you're taking the ratio facts, like being twice as massive as seriously, and using that to kind of construct the structure of your whole space of masses. Good, so these are going to be kind of our three building blocks as far as scalar quantities go. But we don't just want, scalar quantities, we need to be able to do various algebraic operations with scalar quantities. So, the thing that you lose by working with these things rather than the real numbers is that you lose the multiplication operation. So you still have an operation of addition, right? These are, vector spaces or half of a vector space. You can still add things together. But you can't, there's no multiplication operation on these structures, right? And the physical motivation there is, well, if you add two masses together, you get another mass. But if you multiply two masses together, you don't get another mass. But you can, of course, multiply two masses together. It's just that the result is a mass squared, not a mass. You can, if you multiply two lengths together, you get an area. If you multiply a speed by a mass, you get a momentum magnitude. So we need to be able to do these kinds of, we need to be able to multiply scalar quantities together. And what we ought to get is a new scalar quantity as the output. And refer to this as the tensor product of these scalar quantities, which, because it is a tensor product, basically. How does that look? So this is sort of the intuition. So what we're going to do is we're going to define this A tensor B by letting the elements of it just be of the form, A tensor B. So I'll just write it as a pair, A times B, but we impose this kind of condition. So really what we're doing is we're first of all taking the Cartesian product of A with B, and then we're quotienting by demanding that this equality holds. So this here is what you get by acting on A with some real number x, or positive real number x, and similarly, that's just the same as what you get if you do the same thing multiplying it by B. What that sort of looks like intuitively is that, this is your Cartesian product, then the elements of A tensor B will sort of correspond roughly to these kinds of lines. And so what you end up with is, again, a sort of one-dimensional space consisting of all of these lines. Those of you who are more from kind of logic, foundations of mathematics type setup, this is very, very like what one does to define the, is it the rationals you define like this? Sorry, I've had a complete blank. I think it's the rational numbers, where you...
I need the quotient, something like that.
Sorry, that was in an earlier version of the talk that I assumed I wouldn't forget. Never mind. Anyway, this is like one of those construction. Blame jet lag. Good, and so, right. So that gives you the underlying set. That's obviously not terribly interesting, that's just a set. But once you've got that definition, you can then introduce an action of the real numbers or an action of the positive real numbers onto this thing that you've just defined by just defining the action on the tensor product of A with B to just be the result of acting on either A or B. And of course, we've just demanded that those things come out to be the same. Work this through, it turns out that that then makes A tensor B into a scalar quantity. What kind of a scalar quantity? I mean, this is maybe getting a little bit into the weeds, but there's a few possible outcomes. I mean, they're mostly pretty intuitive. So if you take two positive scalar quantities, then the result of taking their tensor product is also a positive scalar quantity. If you do a positive scalar quantity with a full scalar quantity, you get another full scalar quantity. So here, the tensor product of mass with electric charge is also itself a full scalar quantity. If there's an orientation, then on either, then you pick that up. Similarly, when you do two full scalar quantities together, you also get a full scalar quantity, and if they're both signed, then the result is signed. I just thought that if one of them was signed, the result would also be signed, but I don't know, we need to think about it. We need to double check that. The only one that's really going to matter is that if you take the tensor product of a full scalar quantity with itself, that is also itself a signed scalar quantity because you can introduce a natural orientation by saying, by demanding that A tensor A is always going to be positive, right? And A tensor negative A is always going to be negative. So there's a natural way to introduce an orientation. That's going to become important in a moment. Okay, slightly more interesting, powerful kind of thing you can do is also take powers of scalar quantities. So this you can't, so, because we don't want to just multiply scalar quantities together, we also want to square them or take square roots or this kind of thing. So here, I mean, it's a very similar sort of move. So step one is we just define the underlying set by saying that we've got this scalar quantity P, then elements of which are just lowercase p, then for any real number, the elements of the power quantity will be able to form p, just formally p raised to the r. I mean, that kind of, in some sense, is really just, all this really says is we're going to let the underlying set be in bijective correspondence with the original set. So to every element p of our original scalar quantity, we get an element p to the, that we write p to the r of our new quantity. And then, of course, the interesting bit is going to come out in defining the action of R on that new power quantity. And so we fix that by stipulating that this equality ought to hold. So, basically that taking that xp to the power of R is equal to x to the R raised to the power of R. That defines an action of the real positive reals on our new power quantity, because any positive real number can be expressed in the form x to the R, right? So, so the intuition here is that we start out with our scalar quantity p. What is p squared? It's a collection of magnitudes that is in bijective correspondence. So for every element p here, there's an element p squared. The key difference is that if you've got a pair of quantities in your original scalar, a pair of magnitudes in your original scalar quantity where one is twice the other, their corresponding elements will be such that one is 4 times the other. Similarly, if this was p cubed, then the corresponding things would be 8 times the other. Yes?
Is there a single power quantity for all R, or is it that for each R there's a distinct quantity?
For each R, there's a distinct quantity.
Okay.
Yeah, exactly. So, good. So you get, p squared, p cubed, p to the half, and even, I mean, most of these, so the only ones I think we'll really use are, very briefly make use of the square root right at the end. The other one that we'll use at various points is p to the negative 1, which is kind of like the 1 over p type quantity, right? So where our two elements originally were related, where b was, so for example, if you have two masses where m2 is twice as massive as m1, then the sort of corresponding units in the inverse mass quantity are such that the one corresponding to m2 is half the mass of the one corresponding to m1. So that's again what that thing is supposed to illustrate. For the natural numbers, so where R is in the natural numbers, you can kind of, there's a natural isomorphism between p to the nth power and the n-fold tensor product of p, which is reassuring. Actually, really sorry, it's for non-zero n in the natural numbers. That's true. There is a bit of conceptual difference here. So the intuition here is that you're to think of, for example, the space of m is the scalar quantity of mass. You're to think of m squared as being the space of possible elements of the form m times m. For the tensor product of m with itself, that's the space of possible elements of the form m1 times m2. Okay? So obviously there is a correspondence between these things because if I do 2 times 8, that corresponds to 4 times 4. But nevertheless, there's kind of a conceptual difference. Good. Okay. So that you'll probably be relieved to hear is, as I say, the key things that we're going to use, I think, are, this idea of the inverse power and briefly the idea that you can take square roots of quantities. That's all I want to say about scalar quantities. In terms of vector quantities, we are going to take a vector quantity to be a vector space that's been equipped with a scalar valued inner product, right? So although we often refer to the inner product as the scalar product, in fact, it takes values for real vector spaces to real numbers. But we're going to want to let it take values in some arbitrary scalar quantity. So what that means is that we let it take be a map from pairs of vectors to the tensor product of A with itself, where A here is a full scalar quantity. So what that means is that, and then we demand that it be symmetric, linear, and positive definite. Here. And one observation here is that it takes values in A tensor A, not just A. The reason for that, roughly, is that the inner product, just think of an intuitive example, the inner product of a spatial vector with another spatial vector has units of length squared, not units of length, so it's much more natural to let it take values in the tensor product of A with itself. Also, helpfully, so the fact that A is a signed scalar quantity and hence a full scalar quantity is sort of necessary if you want linearity to work. And moreover, this condition of positive definiteness only makes sense because A is signed. So earlier, a couple of slides ago, I mentioned that if you take any full scalar quantity and take its tensor product with itself, you get a signed scalar quantity in a natural sense. I promised I would use that fact. Here is that fact being used. So whenever you take the inner product of a vector with itself, we're going to demand that live in the positive cone of, this should be A, because A doesn't necessarily have a positive cone, but A tensor A certainly will. Okay? Good. So that is a kind of whistle-stop tour of how to think about scalar and vector quantities without invoking real numbers. So this is what I mean about there being just a certain amount of mathematical interest, that it turns out that just to kind of describe what scalar and vector quantities are like, you have to do a certain amount of non-trivial mathematics. Okay. Right, I didn't update this slide. Just ignore the first two bullet points. We're going to be thinking about differential geometry because that is what this talk is and always was going to be about. So there's the challenge that, so the worry here is that, at least on the face of it, differential geometry seems to use units. So famously, differential geometry doesn't use coordinates, as we've discussed in some detail already at this workshop. But there is a sense in which it kind of looks a bit as though it's at risk of using units. The basic kind of reason why you might think that is that the basic objects that one uses in even very elementary differential geometry, which is all I'm going to talk about, all kind of employ the real numbers. So, coordinate charts are charts to the real, r to the n, even if that's getting quotiented out in a certain sort of way. Scalar fields are maps to the real numbers, and a curve in a manifold is a map from some interval of the real numbers to the manifold. And then at least on the face of it, that means that vector and tensor fields are also going to pick up this kind of reliance upon or dependence upon the real numbers. Good, so let's think about how to do this. Slightly on the fence about whether I even really need to do this bit, because as I say, the use of charts is already something, the fact that differential geometry is free of coordinates, is a pretty strong sign that one doesn't need to really worry about the fact that the charts use real numbers. But just in case you were worried about it, I think there's a natural way to assuage that, which is to take seriously this thing that people often say about differential geometry, which is that a differential manifold is a manifold which looks locally like Euclidean space. And then, next breath, they say, that is to say, it looks locally like r to the n. But, Euclidean space, the space of Euclid is not r to the n, famously. It's instead something like an affine space over a real vector space, okay? So let's just let a chart be any local map to any n-dimensional flat space, okay? Where n is fixed here, obviously. We need all of these to have the same dimensionality. And then, rather than the compatibility condition saying that a certain map from Rn to itself is smooth, that you get by composing two charts, instead we're going to demand that a certain map from, perhaps distinct Euclidean spaces is smooth, where smoothness here is going to be explained using the apparatus of by appealing to the structure of the affine space, that in turn is going to be appealing to the vector space. That in turn is still going to be sort of appealing to smoothness on the real numbers, but I'm not convinced you're going to be able to get rid of smoothness without thinking about the real numbers, at least not without doing some very fancy footwork. Anyway, as I say, I actually don't think this is that significant, because I think the charts weren't something that should have really been worrying us to begin with. Good. Slightly more interesting, though, I think, is thinking about scalar fields, because on the face of it, when you say, a scalar field takes values in the real numbers, you seem to be working in a kind of unit here. Insofar as these are supposed to be representing physical quantities, that seems to be presuming a particular choice of scale. So, so the easy thing is to come up with a better definition of a scalar field. So rather than a real valued map on the manifold, it's going to be just an A-valued map on the manifold, where A is some scalar quantity. I've said smooth there. I mean, again, that's sort of assuming that you can. I haven't quite done this, but given that A is just a one-dimensional vector space, real vector space, or half of a one-dimensional real vector space, you'll be able to, I think, apply just normal definitions of smoothness to cash that out. But of course, in differential geometry, individual scalar fields aren't actually terribly interesting. That's not really what this ties in a little bit actually to some conversations that Dave and I were having. I think my instinct is to say that a manifold doesn't really care that much about individual scalar fields. What it cares about is the algebra of scalar fields, the collection of all scalar fields and the operations between them. This gets a little more subtle because you can't kind of just say, well, think about the algebra. I mean, yes, you could be like, think about the algebra of all possible scalar fields, but that's a bit weird because then it's like the maps to all possible scalar quantities. I think it's better to kind of, just suppose that there are some particular scalar quantities in which we are interested. So we're going to just take a bunch of scalar quantities, A1 through AN, and say, okay, we're just thinking about the scalar fields that take values in those quantities. Then what you do is, I'm glossing over some details here, but roughly take the tensor algebra generated by those quantities. So very roughly, this is going to mean that you have your basic quantities A1 through AN. Then you also have the products of any pair of those quantities with each other or with themselves. You have products of products, products of products of products. Because of the tensor product, you can't, really it's a direct sum of those things. So you also have sums of those. That's really just a sort of bookkeeping device for talking about two different quantities. The important thing is that you get the product. You get all the product quantities that are generatable out of these things. So the idea is that that means that if you've got something phi that takes values in A, and you've got something psi that takes values in B, then you are going to also think about scalar fields that take values in A tensor B, and among those scalar fields is in particular going to be a scalar field that we'll define as being phi tensor psi. Okay, so we're going to now sort of pull the tensor product structure from this tensor algebra on the space of scalar quantities onto the set of scalar fields. So that is going to turn that set of scalar fields itself into an algebra. Okay, good. I think, good. Here's kind of why you would want to do that is, if you're wanting to do differential geometry, you want to think about vector fields. What's a vector field? At least I think the sort of mathematically nicest definition is as a derivation on the algebra of scalar fields. That obviously doesn't work if you don't have an algebra, right? So that's why I think it's important that we get this algebra of kind of intrinsic scalar fields. But the nice thing is that since we've got that now, we can define what it is for something to be a derivation. So it's going to be a linear map which obeys Leibniz's law. So it acts on phi tensor psi to give you x of phi tensor psi plus phi tensor x of psi. Okay? Good. Having done this, so what we've kind of now done is we started out with the standard notion of a scalar field. We then generalized that to allow scalar fields to live in arbitrary scalar quantities. We've also, at least on the face of it, then come up with a certain generalization of the notion of vector field, where now there are derivations on arbitrary algebras of scalar quantities, of these sort of intrinsic scalar fields. However, I think, and this is not something that this is something I like sketched a proof of yesterday morning while very jet lagged. So I think this is right, but yeah, if somebody thinks it's false, please do tell me. I think the thought of this is that you in fact get the same vector fields that you had to begin with, right? So the normal vector fields on your differential manifold, in fact, coincide with vector fields defined in this new way. Why is that? Because I think there's a kind of natural scale-independent bijective correspondence you can set up between these new vector fields that are derivations on this like fancy algebra with the vector fields that you know and love. So how does that go? So suppose that you've got a vector field in this new sense, x, taking you from between these two tensor algebras. Just for each of your scalar quantities, a1 through a, pick a scale, that is to say a linear, a vector space isomorphism from ai to r. And then let S be roughly what you get by kind of taking tensor products of all those maps together such that this applies to the whole tensor algebra. If you then take any kind of normal real scalar function in the old sense, so just a real value map on your manifold, precompose it with your with the inverse of this kind of big fancy scale, that's going to convert it into a map that will take values in this tensor algebra. That means you can apply this new kind of vector field, and then what you can do is you can again precompose it with your scale effectively to get back another real valued scalar function. So the thought here roughly, so the thought, and then I think, having kind of, as I say, sketched this out in my notebook, I think what effectively ends up happening is that the choice of S sort of drops out. So even if you were to use a different field, a different scale, set of scales Ti, then you would end up kind of with the same bijective correspondence between new vector fields and old vector fields. I think this is right in part because it also then tracks a certain kind of intuition. So if you think about what a vector field is doing, at least in this kind of picture, it is sort of saying to you, it's comparing, this is very rough, but you sort of think of it as saying, well, take the scalar field at this point here, take the scalar field at this point here, what's the, is that right? Yeah, what's the magnitude of the difference between them? If say originally we had a scalar field which takes the value kind of 2 here and 4 here, it's going to return the answer 2. And if I rescale, then I get kind of 4 here and 8 here, so I get the answer 4. So the difference is also itself just scaled by 2. It's scaled by the same factor. And I think the fact that these differences scale in the same way as the scalar fields themselves, I think is sort of a reason why intuitively we should think that vector fields don't, again, the vector fields that we had to begin with were kind of okay. Good. So this is in some ways, now I say it all out loud, it's in some ways, so what I think we've established so far is that charts, it turns out, don't actually really have a dependence on units. Vector fields, it turns out, don't really have a dependence on units. Scalar fields do, but in a way that's relatively easy to handle. So this is all kind of looking fairly promising. A more interesting case, I think, is thinking about curves through a manifold. So again, recall that the usual way of doing this is to say that a curve is going to be a map from some interval of the real numbers into the manifold. So we're just going to do that, except we'll replace the real numbers by an affine space over some signed scalar quantity A. So that affine space is T. It's an affine space rather than just A itself because it doesn't need to be A itself. It just needs to be such that distances between points in T are measured by A. So let's use the slightly weaker thing. And yeah, the reason why I've made A signed, there's kind of a particular reason to demand that A be signed, which I will talk about now. So that part is pretty easy. This is a bit like, just defining what a scalar field is. It's sort of, an obvious definition to do. Where life gets interesting is if you think, okay, what do I do with curves? Well, I take tangent vectors of them. So let's see if we can do that. Let's see if we can make tangents. So this is going to be basically the same sort of thing. So at any point gamma of t, we are going to define for any b-valued scalar field phi, so phi taking values in the scalar quantity b, this hopefully pretty familiar looking definition where gamma dot of phi at the point gamma of t, just left implicit, is also taking this particular ratio in the limit as a goes to 0. Now, I've slightly cheated in writing this on the board, partly to keep it fairly concise and partly to make it look familiar. Is there a whiteboard marker somewhere? Something over here, probably. Yeah, here we go. So I've cheated slightly by doing it this way because, I haven't actually defined ratios, right? So you might be thinking, well, what does that mean? Well, really, it's actually just elliptical for so it's limit as a goes to 0 of gamma of phi of gamma of t plus a minus phi of gamma of t a to the negative 1. Right, so that's the kind of formally correct expression given the apparatus I outlined earlier. And so A here is taking values in the positive cone of n. That's why you need A to be signed, okay? Because if A isn't signed, then it doesn't have a positive cone. So you don't know, as it were, which A you ought to be taking. Why does it have to be in the positive cone? Because you want to take the inverse of it, and at least with the apparatus I've laid out so far, that's only well defined for positive quantities. I think the slightly more subtle thing that's going on here is that if A isn't signed, then in a certain sense it's not obvious which direction the tangent vector ought to point in. Okay, so this actually is a point that Field touches on in his book and David Malman actually makes in his paper on time reversal and classical electromagnetism, which is roughly that if you have a curve through a manifold, so parameterized by, in general parameterized by the real numbers, the definition of a tangent vector, so the association of a tangent vector to a point on that curve, non-trivially exploits the fact that R is an oriented vector space. So the fact that R comes equipped with a natural, because that's what tells you that you want to identify it as this vector rather than this vector. Right? Like you need to know which direction, or in slightly more physical terms, if you think of this as a trajectory, in order to associate a tangent vector to each point on the curve, i.e. a velocity, you need an underlying temporal orientation to tell you which direction is future, because if you switch the temporal orientation, the velocity vector is flipped pointing in the other direction, right? So this is basically the fact that A has to be signed is, I think, just tracking that observation about velocities. Good. Note, however, that because this whole thing is a limit of an expression of this form. Again, I'm sort of assuming I can just take limits of this. I haven't checked that, but probably fine. Then
We'll make a physicist of you yet.
Clearly this thing lives in B, right? Because phi takes values in B, and we've just taken the difference of two things that live in B. This thing clearly in the inverse of A. So this whole thing lives in B tensor A inverse. What that means, slightly oddly, right? So I told you a moment ago, I defined vector fields as being a derivation on the algebra of scalar fields. A derivation on phi would live just in B itself, right, with the definitions I used a moment ago. Live in B, it lives in B tensor A inverse. And what that means is that it is not a vector in the sense outlined above. Okay? So there's a sense in which, on this kind of approach, the identification of tangent vectors with derivations on a set of scalar fields kind of breaks down. Okay, so we can still define, or slightly more carefully, so we can still define a vector field as a derivation on the algebra of scalar fields. We can identify tangent vectors for curves parameterized by the real numbers with those things, but for curves parameterized by arbitrary other quantities, we can't. Now that sounds bad, but I think it is in fact good. The reason for that is that, again, so if you sort of think ahead a couple of steps to an application of this, maybe you want your manifold to represent space, right? A possibly curved physical space. And maybe you want your parameterizing space T to represent time. It's not a completely somewhat tendentious choice of notation here. Then you're going to want tangent vectors to that curve to have units of speed, right? So length over time. And so whereas a derivation on, so whereas if you just had a, right, sorry, there's actually a further subtlety here. So this thing, gamma dot of phi, is going to take values in B tensor A inverse. Gamma dot ends up kind of just taking values in A inverse, right? So it doesn't really live in, in B tensor A inverse. It is instead kind of just, so anyway, but this is one of the things that I was doing this morning. It's still, so this is very kind of rough and ready, but the intuition here, at least for me, is that we're picking up a kind of 1 over time sort of factor in a way that I think is in fact good and represents sort of roughly what we would want. At least looking ahead to more physical applications. Good. Okay. Final thing that I want to talk about today, probably be relieved to hear, is how do we extend this to thinking about Riemannian geometry? So this, I mean, given what we've done so far, is I think in some ways pretty natural. So and normally a metric is an inner product of this. We're going to let an A-valued metric be an A-valued inner product on each tangent space. So, I mean, I told you already what an A-valued inner product was, so we're just going to use that. What that means is that we are going to, so given a T-parameterized curve, we then define the length of gamma between any two kind of points in our space T by integrating, write down an expression that looks identical to the expression that you would have done if you hadn't attended this talk at all, but is in fact importantly different. Because it allows us to kind of check for the legitimacy a bit more carefully. So, so D is A-valued, so this thing takes values in A. Because it is an inner product, and because the definition of an inner product demands that when you take the inner product of something with itself, you land in the positive cone. That means that taking powers of that is legitimate, in particular taking fractional powers of it is legitimate, so you can take its square root. So the whole thing that results is, this doesn't look good, wait. Hang on. Okay. Sorry, this is something I need to think about more, because this, on the face of it, is giving us a factor, is giving us a T factor. Oh no, hang on, this seems right. So yeah, I think the gamma dots will each have a factor of kind of T to the negative 1. Because we've got 2 of them, that's going to give us, I think, T to the negative 2. The square root should give us T to the negative 1 again, and then the dt is going to give us a factor of T. So this thing ends up just taking values in A. So the T dependence sort of drops out. But this is what I mean about the conceptual hygiene, that we have to kind of, we're forced to be careful in a way that I've not been in preparing these slides. Good. So yeah, and that's I mean, this, in case you're wondering about the image, this is the stock image that Apple Keynote presents for this theme. It has nothing to do with this slide. Good. So yeah, here's the conclusions. So we can remove the dependency on the real numbers, at least from the kind of elementary parts of differential geometry. Turns out that, yeah, like charts and vector fields, this doesn't actually make that much difference. But it does seem to make curves kind of, I don't know, thinking about what to do about curves is a bit tricky. And in particular, the way in which we normally code up information about tangents to curves as vectors turns out to be kind of problematic or tricky, albeit in a way that I think it, in fact, might be physically, required, because ultimately we think, to some extent, actually here's a simpler way of making that point. Normally we have a bunch of different kinds of vectors, right? So we have spatial displacements. Spatial displacement is a vector. Velocities are vectors, accelerations are vectors. All of those things have different units. So it's very weird that they all live in the same space. And so the fact that we get this problematization, I think, is actually pointing to is sort of a feature, not a bug. Nevertheless, we're able to, broadly speaking, make sense of the notion of the metric, which hopefully should mean that we can move toward thinking about Lagrangian mechanics. Since we've also been talking a lot about spacetime, I should note that doing it for a Lorentzian metric, I think, is much, much harder because you have sort of two different kinds of quantity going on there. But again, that seems to me to suggest that this notion is more subtle than our usual formalism might suggest. That type of thing. Thank you very much.
Time for questions. David and Penny.
I want to wonder if the elimination of the real numbers from the manifold is really necessary, even in terms of the project. I mean, thinking first about the coordinate charts, and there were bits unsure of this anyway. I mean, a lot of the point of this coordinate chart, just linked back to Thomas's talk yesterday, a lot of the point of this coordinate chart way of characterizing the manifold is we're declaring lots of the structure of the chart thing irrelevant precisely by our flexibility and promiscuity to the charts.
Right.
So even in this case, you can use an affine space here, but the affine structure is irrelevant.
Yeah.
And the tell that the affine structure is irrelevant is that we allow charts that differ not by affine maps, but by smooth maps. There's a perfectly well-defined mathematical object genuinely defined by affine charts, and affine maps clean them. But it isn't a manifold. It isn't a differential manifold. So it sort of feels like, if you want to be intrinsic, the right object to use your charts is a differential manifold or something. But
Yeah.
And then I sort of feel similarly when you look at the way you're defining the way you want affine functions, scalar function spaces. I mean, again, given that we've got all the real functions, then it doesn't seem that we're building in any particular length. And on top of that, you've got the fact that I think the genuine real functions of the manifold fill a perfectly useful mathematical role. I mean, sometimes we want to multiply a vector by a real function. And it matters that we don't want to map the vector to something in a different, larger scalar space. We just want to multiply it by a. So, I can say somewhat similar things about getting rid of the scale on the curves. I just sort of think it's not. It feels like it might be a bit premature to be trying to eliminate at this stage in the process.
That might be right. Yeah. So Good. So, there's a sense in which, right, so first of all, just on the chart, I sort of went back and forth on this, about whether to talk about this. One worry about not doing it is that, in a sense, the idea, we're going to get rid of the structure by just letting ourselves be promiscuous about which chart you use, is exactly how in much more elementary physics we would sort of get rid of the unit dependency here. So we represent mass by real numbers, but we say, look, you can choose whatever scale of the real numbers you like. So there's a sense of which, partly just dialectically, if I'm allowing it there, then it problematizes, it makes the project as a whole, or it's perhaps in tension with the sort of way that I'm doing the project as a whole. Does that make sense?
It does. Well, put it this way, maybe there's a tension between the whole Kleinian way of characterizing a geometry via lots of maps and the intrinsic property project.
That
But if there
might be
is, I
right,
don't
yeah.
think you can solve the problem just by using Athon spaces.
Yes,
Usually something
good,
like you need
good.
intrinsic characterization of
Yeah.
differential manifolds.
Yeah, that's probably right, actually. It's geared to, it's good. Yes, I think that sounds right.
I mean, I think we shouldn't be scared of Kleinian characterizations, but
Yeah.
if one was, then I think
Yeah.
you have to do something more substantial.
Right, and I mean, I also agree that we should characterizations. This is kind of, yeah, as I say, this is in some ways like just what is the non-Kleinian characterization of scalar quantities. Yeah, on the intrinsic scalar fields, yeah, good. I mean, the motivation here is sort of in some ways quite flat-footed. That look, sometimes, I mean, at least some of these fields are will have kind of physical interpretations. Like you might have like a temperature field or something. And so we ought to be able to kind of handle that. I mean, the fact that when you sort of, this might be your point, but about the stage of the project, that having sort of faffed around with all this stuff, I'm now kind of tempted to think, well, look, yeah, actually, in terms of like getting the apparatus of differential geometry going, defining what a vector field is, you don't need to sort of worry about it at this stage. What you actually need to do is just define vector field as you did normally, and then just explain how it is that you take a derivation of a scalar quantity valued scalar field rather than just real valued scalar fields.
Right, and look, a scalar field is a vector field in a one-dimensional vector space to be distinguished from a real field.
Right. Yeah, exactly. Yeah, so that's effectively, that's probably the way that I will in fact do it. Good. Cool, thank you.
Can you go to the slide where you had the T parameterized path? Yeah, so I wasn't convinced that we need A to be signed here. It seems that, I think, like, how did so for one thing, you defined when you originally defined the inverse, you did that as part of this instance of defining like R powers for any real valued R. And for the non-integer powers, it matters that you'll be but for integer values, it looks like we should be able to take integer powers, including negative integer powers of a full vector scalar. And here, I think, in the case where phi is an A-valued scalar, then we're going to get a signed thing when we take A tensor A inverse, right?
Sorry, phi here is B-valued.
Right, but if B happens to be the same value as A,
Good.
then we'll get a signed thing. But in the case where it isn't, we don't get a signed thing. And I think in the case where it isn't, it's not obvious to me that we care which direction the vector is pointing. We just need to know when it's pointing the same direction and when it's pointing the opposite direction.
Yeah, good. Yeah, good. So I think on your first point, I think you're right. The fact that we have to take an inverse of A, I think, is irrelevant. I think I've gone back and forth on this. I think the difficulty that one runs into is, right, so if A is not signed,
And B is a distinct scalar field.
yeah, so just thinking about this case, then
Like imagine if A is like an unsigned time quantity and B is just a spatial thing or something, then it seems like we care when B over A is the same sign as what it was at some other point and when it's the opposite sign of what it was at some other point, but not necessarily which sign it is.
So just taking kind of a geometric intuition. So suppose that, suppose that, so these are the surfaces of constant phi, increasing towards, so let's say this is phi point. So we're here, and we've got a curve. This, and so the intuition is that the tangent vector is an object which, will. Yeah, so no, I think A does need to be signed because otherwise I think this construction, this definition comes out ambiguous. So if okay, so here's maybe a way to try and show that. Think about two different orientations on A. So suppose we give A an orientation such that like this is the the tangent vector at this point, let's say at this point here, will be such that when you feed it phi, you get a positive answer. And on the other hand, if if this is the positive direction, then the tangent vector will be such that when you feed it phi, you get a negative answer. So, but the tangent vector is to be a well-defined derivation on the set of scalar fields. It has to either give you a positive answer or a negative answer. Does that make sense?
I think only if the space B tensor A inverse is itself signed.
Well, so it's yeah, good.
Yeah, so when A is signed, you should end up with a signed thing here.
Yeah,
But when A is not signed, it seems fine that
good.
you end up with an unsigned thing.
Yeah, good. So if B is signed or positive, I suppose, because positive scalar quantities are trivially signed.
Yeah.
Yeah, good. That sounds right. Yeah, okay. That seems plausible, but I'm going to need to think about it more and probably draw a lot more diagrams. Good, thank you.
Emily?
Yeah.
I was going to ask something similar, so
Okay,
that's
cool.
covered my question.
Any other questions? We do actually have just a couple of minutes, so I'm gonna ask one. I was struck when you were talking about C infinity of M, and what you end up with here is a graded algebra and not an algebra, which is a bit different from what we normally have. And it does make some things kind of weird. And I think this is connected to David's question because, in an algebra, you can ask things like, what is A times B quantity plus C? And here, you can't. You can only ask what's A times B plus, well, you don't get something that has the same height as the individual things.
Yeah.
And at least sometimes I think it's important for characterizing geometry that the elements of C infinity of M are not signed, or no, that's not what I mean. I mean,
Are not
like
graded.
don't have units.
Yeah.
And so here's just an interesting mathematical question you might ask. If you give me a graded algebra, can you characterize the properties that algebra would have to have such that it has representation as the graded algebra of scalar quantities associated with some A on a manifold M? And I'm worried that the standard way of doing that sort of takes for granted that you actually have an algebra.
Good. I mean, so you will. Okay, so I don't know if this is going to assuage your worries. I mean, you will still have like a kind of A tensor B plus C type thing. So the plus there will be sort of direct sum. There's not a combinability. It doesn't merge with A tensor B. But you can still apply X to it. It's just that where X will act separate. I think this is right. X will act separately on A tensor B and C. Never the twain shall meet.
Yeah, well, let me give you an example of where this can look kind of weird.
Yeah.
So how am I supposed to think about the maximal ideals of this algebra? Are they fields that vanish at a point? Or are they fields that vanish at a point and all tensor products that include fields that vanish at a point? I think it has to be the latter.
So you'd start by considering or perhaps saying out loud what the definition of the maximal ideal is.
A maximal ideal?
Yeah.
Oh, so it's a subalgebra that's closed under multiplication by other elements of the algebra.
Yeah.
By any element of the algebra. And so in C infinity of M, normally it's the scalar fields that vanish at one point.
Good.
And it may just be that it's totally simple, that it is something like just the things generated by all of the, that vanish at a point, or multiplied by something that vanish at a point, or that multiply. But like there's kind of an elegance to the way that you normally do it, because when you multiply a scalar field by another scalar field, if it vanishes at one point, the product also vanishes at that point.
Yeah.
And here, that's not really what's going on anymore. What you have is you put in by hand that these other things that you get in the tensor product are also there.
Yeah, good.
And I don't know if that matters, but it is kind of a changing the structure of C infinity of M.
Yeah. Yeah, good. So, yeah, I mean, I would need to think about this more, but one thing that I've been struck by in this project is how inelegant a lot of it is. Just not ideal. But although, I mean, maybe again speaks to an interesting, speaks to part of the role of mathematics is, yeah, I mean, kind of filling in gaps. The terms Toby was using yesterday, like part of what I feel happens. I don't know, actually, I mean, this is, the idea of like adjoining ideal elements in order to give a more elegant kind of treatment is very, obviously, like internally to mathematics, very, very standard. And I feel like that's sometimes part of what's going on here is that when you, weaken the structures in the sorts of ways I'm playing with, you end up with stuff that can feel less unified and less tractable. And yeah, that it perhaps points to like a slightly different, it feels like a slightly different character, like calculational convenience, which is the thing people often say about why use the real numbers. It's something more like just mathematical tractability. Maybe it's that different. But yeah, I don't know.
I wonder though if there's another perspective where you say something like, there's something really physically important about dimensionless quantities. And one of the things that's important about them physically is that they can provide kind of a scaffold for representing these structures. And then for various purposes, and when we're thinking about measurements and stuff like that, we need to sort of break those apart and reintroduce the dimensional quantities. But it's not necessarily somehow non-intrinsic to be judicious in our choice of what quantities what structures in the first place.
Good, and again, to track David's comment on like, what's the stage at which you want to introduce this stuff? Yeah, and it's making me wonder if actually the thing to do is like not stress about making stuff intrinsic. It's sort of scaffolding only really when you start, particularly when you introduce a metric, that is when you're going to have to start worrying about units, at least insofar as you're doing this metric physical interpretation. But maybe that's the point at which to start using this sort of apparatus. Good. Cool.
Yeah, I'm kind of reminded of, like there are these exercises that people who really like dimension-free quantities talk about, like in the context of GR. Where it's like, can you